T-minus 15 seconds. T-minus 10, 9, 8, 7, 6. We have main engine start. 4, 3, 2, 1, and liftoff. Liftoff of the 25th Space Shuttle mission, and it has cleared the tower.
What you just saw was moments before the Space Shuttle Challenger explosion due to both communication and mechanical errors. We would just like to start off by saying we express our sincere condolences for the 7 lives lost on that day. The gravity of this event is not lost on us, and we hope we can convey the necessary standards of quality, communication, and safety necessary to prevent tragedies like this to you.
One of the major reasons for the explosion was a lack of communication among the shuttle team. What occurred was a group of contracted engineers from Morton Thiokol were acutely aware that something was going to go wrong on the day of the launch. On that day, the weather was much worse than it had been on previous days. When the engineers told the launch crew that the launch was going to go bad, they were told to sign off on the launch anyway. This was due to the fact that a lot of pressure was on NASA when it came to the launch happening. Not only was the US racing with the USSR at the time to improve space travel, they had already pushed back the launch day due to weather conditions before. So this time, due to all the pressures on them for the launch to happen, they okayed the launch, even though they were aware of the risk causing the rocket to unfortunately explode, taking the 7 lives that day. This extreme lack of communication, which resulted in the disaster, then resulted in all flights being grounded until a presidential investigation into the causes of the disaster had been concluded and a new policy was instilled. The most significant change in policy was the mandate that another such warning against a launch would not be ignored by management. As a result of this policy change, NASA has never experienced another disaster of a caliber anywhere near as serious as that of the Challenger disaster as a result of poor internal communication.
Now for the mechanical side of why the Space Shuttle Challenger explosion occurred. The main failure that occurred on the day of the launch was due to the O-rings. On the day of the launch, the outside temperature was about 2 degrees Celsius or 36 degrees Fahrenheit. This cold temperature made the O-rings, pieces that were meant to prevent fuel from escaping the fuel tank, less effective by hardening the rubber, which resulted in their failure to expand and form a seal. The O-ring failure created a fuel leak, which ultimately led to the catastrophic explosion. Because the O-rings weren't able to handle the cold temperatures, NASA developed more strict guidelines for the O-ring designs. These guidelines included using 3 O-rings instead of 2, the addition of heaters to stabilize the O-rings for temperature below a certain threshold, and the use of more elastic materials. NASA looked for more elastic materials that also prevented the buildup of electrical charges so they could be used to avoid ignition in the fuel lines. As a result of these changes, there has not been a recorded mission failure in which O-rings were at fault since the Challenger disaster.
This change in design is what engineering and science are all about. This is where we'll have you do a hands-on activity where you will create a model spacecraft and make different designs work more efficiently. So for this project, what we're going to have is we have our materials. We have 2 index cards. This is where you're going to be drawing your design. Then you have your 2 cutting tools, which are your scissors and your knives. Then you have your pencil to draw, of course, and your straw. This is where you're going to be attaching your design. So as I move everything out, we're going to now draw our design. So I would do just a quick draw. You can be as neat. You can do whatever design you want for your spacecraft. So you see here I'm doing the Challenger with the smoke cloud. And of course you're going to do it on both sides, so then you can cut them out individually and have your pinwheel. So now, after you cut them out from your index cards, you're going to see that I have 4 individual parts here, 2 for the Space Shuttle and 2 for the clouds. So now what you're going to do is you're going to either take the knife, very carefully of course. If you don't have a knife, you're going to use scissors. And you're going to cut along so you can place these blades for your pinwheel onto the straw. And like I said, we're going to use the scissors if we do not have a knife. And then you're going to make a slit and cut up if you need to get lower. And now, once they're cut, you're going to apply the blades into the straw. And you could do it at any angle, any way that you want your pinwheel to be. Another thing you could do when you're cutting, so there's 2 ways you could do it. You could either cut them out individually, like this, or you can cut them out as one. And once you do that together, it'll come out to look something like this, and your pinwheel will be ready. You're going to attach a string to it, And now you have completed your pinwheel.
Thank you for your time. We hope that this video has been informative and that you've enjoyed learning about the role that communication plays in safety and in science. Additionally, we hope that you were able to build your very own rocket model at home and get some insight into the process of what building a real rocket is like. This is a topic that is very near and dear to our hearts, and we are glad we got to share it with you today. Have a good day.